in the direction to that of angular velocity. As it is retardation, the direction should be negative to that of angular velocity. Here it is given angular velocity is counterclockwise. So the angular retardation will be clockwise for the link AB. That is angular acceleration for link AB. Alpha 2 will be opposite in direction to the angular velocity. So alpha 2 is clockwise. It is clockwise. Then we have to find the sense or the direction for alpha 3 and alpha 4. That is the angular acceleration or retardation for the links 3 and 4. So it is nothing is mentioned in the question. Only about the link AB is mentioned in the question. That is, the velocity is counterclockwise and the acceleration and the other two links are not mentioned. Its directions are not mentioned. So we'll go through the acceleration diagram. Here the centripetal acceleration for BC, here it is drawn, that is FCBC, here it is drawn, and the tangential part is drawn, and we got from the figure that it is going upwards. Similarly, for the link CD, the centripetal acceleration part is this, and the tangential acceleration is going upwards, which we got from the figure. So both are going upwards, and this is the tangential acceleration for AB, and it was going downward. So this is, if this is clockwise, as I mentioned, as the velocity for this link is counterclockwise and the acceleration is retardation and is going downwards and it is clockwise, here we got the tangential acceleration for the other two links are going upwards, and therefore those two links are counterclockwise. Okay, counterclockwise. And again, now we have to find the values of this alpha 3 and alpha 4, that is FTCB by CB, which we know. 22.5 is the value of the tangential part, which we just got from here. The tangential part for BC, that is FT BC, divided by the length of the link BC, which we know is 0.66. So it will be 34.1 rad per second square, and it will be counterclockwise. And again, alpha 4 is FT CD by CD equals 44.3 by 0.56, which will be 79.1 rad per second square, and it will be counterclockwise. So also we know about the inertia coupled. You can represent it as CI. It is moment of inertia I into angular acceleration. So for the link AB, moment of inertia I is given. It is given in the question. That is 88,500 kilogram meter square. So 88,500 kilogram meter square. Also we know the equation for the moment of inertia, mk square. From that we will get the value for k square. So this is the link 2, so we can mark it as k2 square. So k2 square equal to I by m equals 88,500 by the mass of the link 2, that is given to us 3.54, and the value will be 25,000 millimeter square. Millimeter square. It's not meter square, it's in millimeter square. In the question it is millimeter square, so it has to be in millimeter square, and it is 25,000 millimeter square. Now, as the moment of inertia for BC and CD are not given, then K3 square and K4 square has to be found out in another manner. As all the links are rectangular in shape and both are uniform, we can use the equation K3 square equal to L square by 12, where L is the length of the links. So L is 660 millimeter. As we are now converting it into millimeter square, again we have to do it in millimeter. That is 660 square by 12. It will be 36,300 millimeter square. Similarly, K4 square is L square by 12 equals 560 square by 12. It will be 26,133 millimeter square. Now, we have found the forces acting on the center of mass of these links, but the inertia couple is not taken into account. The inertia couple is not taken into account to determine the actual center of mass of each links. For that, we have to find the equivalent offset inertia force that will represent the impact of the inertia couple in the links, so that the center of mass of each link can be drawn to a new distance, and the new distance has to be found out, because as it is a couple, we can mark the forces and the direction, and its direction we have already found out. It can be transferred to the particular distance which will give the impact of the inertia couple in the entire system. So that's why we are finding a new distance. The offset distance means the parallel distance. The parallel distance. So the steps involved are, first we have to find the perpendicular distance h from each forces. The perpendicular distance from h for each forces, that is, for example, consider this as the link AB, and the force which we got, it has F2 as 80 Newton. 80 Newton and is angle 253 from the fixed link which we drew from the acceleration diagram. 253 means it can be represented as, this is the fixed link, this is 180 minus, in fact 253 minus 180.5 minus 180, it will be 73.5. So it will be 73.5 degrees. Okay, so this was the original center of mass which was given in the question, that is 200 mm from the fixed point A. So we have to consider the inertia couple acting on this link, that is taking this force, we have to draw a perpendicular from this force. So this is the force, that is 80 Newton angle 73.5 to the surface. Okay, and this was the link AB. So this is the point G2, that is the G2. Okay, so we have to find the offset distance by drawing a perpendicular from the force and extending. Will get a point that is meeting the link A. Okay, now we can easily calculate the angle here, which we will be getting as, it will be around 13.5 degrees, which we can mention in the figure. So the force have to act 73.5 to the surface, so we have to mark it here. So we will be first drawing a parallel distance from here and to downwards to here. Now it has to be 73.5 inclined to the surface. So I will explain it in a much more elaborate way. Guys, consider this was the link AB, this is the point G2, and we have to, and this is the surface, that is AD. Then the force will be acting, it will be 73.5 to the surface. So first we will be drawing dotted lines from here parallel to the surface, and again perpendicular down to the surface, and we know the force is acting 73.5. So we can mark 90 minus 73.5, that is 16.5 16.5 16.5 from here to 90. So exact 90 will be somewhere around here, So in order to get a 73.5, we can measure 90 minus 73.5. It will be 16.5 and can be marked just like that. So this will be 73.5. Okay. Similarly, we can draw all the forces acting to this point. This is 73.5 and this was the .330. So this was G3 and this was 280 G4. You can always draw parallel. This was G3, right? This was G3. This is G3, just like that. This will be a much easier method. So this will be 238 minus 180 will be 58 degrees. Again, the fourth link can be transferred to here. Just like this. It will be 42 degrees. G4 will be 40 degrees. So now we have to find this h, that is the height, the perpendicular height from the forces, perpendicular from the forces. We can use the equation k square alpha by acceleration k square alpha by F by G2, that is the point where the center of mass acts. So K2 square we have already found out, it was 25,000 into alpha 2, it is 26 meter per second square. No, it's 26 rad per second square divided by the distance. That's the distance. It was around alpha 2 was given, it was 26 divided by G2 is the distance, it will be 22.5. here G2 is 22.5 meter per second square. Now we have to convert that into millimeter, that is 22,500. It will be getting around 28.8 millimeter. And H3 similarly K3 square alpha 3 by G3 equals 36,300 into 34.1 by, it was 52 meter per second square, so 52,000 will be 23.8 millimeter. And H4 K4 square alpha 4 by G4 equals plus 25. So K4 was 26,133 into alpha 4, which we got to 79.1. Alpha 4 was 79.1 divided by G4, that is 25,000, and it will be 80 millimeter, so 80.4 to be exact millimeter. Now you have to find the original offset distance. So for the link AB, this was the initial point for G2 and the force was acting around like this. And now you have to find the offset distance, how much distance should be considered in order to take care of the inertia couple. So it can be either upwards or downwards. The offset distance will be a parallel line to the force acting. So this was the force acting initially at G2, it will be represented in dotted lines, and the new force or the new center of mass of the force can be determined by using trigonometry, which we are mentioning here. This is the distance should be found out. So we know, as the link was initially in 60 degree and the force acting was 73.5, which we can easily represent in the figure, and then this angle, as I said, is 13.5 degrees. So by extending a perpendicular from the force, we will be getting the distance H2. This is H2. So H2 we have found out it as 28.8 millimeter. 28.8 millimeter. So we can take sine for this angle, the included angle, which we get from the diagram. This can be measured in the diagram. also this angle, and also for the link BC it can be measured. Here also it can be measured. Similarly, here it can be measured. So sine for this 13.5 equal to opposite side, that is 28.8 divided by the hypotenuse. The hypotenuse, this hypotenuse is the offset distance on link, that is this distance. Okay, so the offset distance equals 28.8 divided by sine 13.5. It will be 125 mm. Now there arises one confusion to where the offset should be done, either upwards or downwards. So for that we are drawing again a rough figure of our diagram, and we have found out the acceleration. The acceleration was clockwise. Thus clockwise, the tangential acceleration we got was going downwards, and it was mentioned here in the same direction, and it was clockwise. And we found out the other two, alpha 3 and alpha 4, were counterclockwise. So counterclockwise for link BC, counterclockwise means it is going like this, and for link CD, counterclockwise means acting opposite like this. Okay, so for link AB it is clockwise. The force will be the original force, considering the inertia couple, the original force will be acting like this, and here the original force will be acting similarly, and here also similarly, and we will get to that. First we will finish this. Okay, so it is the offset distance we have found out, and we have found out the original force should be acting from here to a particular distance, from the force to a particular distance. That is, the new offset for link AB should be, we can represent as R2 as the center of mass of the link, the original value of the center of mass of the link from A, and the new force will be acting slightly upper. It will be like this, upper. So this is. So the new force will be upper, and the force will be acting like this. So as it is upper from link A, it should be added. That is, thus the offset distance 28.8 by sine 13.5, that is equal to 200 plus 125 equals 325 mm. This should be from A. That is, I'll explain one more time. This is the link, and the original force should be acting from that point to the clockwise direction. That is, it should be like this, and so the offset distance, this was the original point G2. It has changed, and 125 mm is the offset distance, and it can be represented as 125 mm either upwards or downwards. So as it is clockwise, the original force will be acting at a upper side of the given point, because it should be acting in clockwise direction, so it should be upwards. This is for the link AB, and similarly for the link BC, as it was acting, it was previously acting at, yes, this is for the reference. It was acting like this, and the new force, this was G3, the midpoint, and the new force should be acting from here to here, that is, this is the anti-clockwise direction. So this should be anti-clockwise direction, the new force should be anti-clockwise direction, which means we have to, anti-clockwise direction means the new force should be like this. From here it should be anti-clockwise direction, it should be below, the offset should be below G3. The original center of mass due to inertia couple should be below G3, and it should be acting like this. We'll get to that one more time. That is the new offset for link BC. This is the, suppose this is the link BC, and this was the midpoint G3, and here what I have mentioned is that it is counterclockwise, so it should be acting like this. So the new offset distance, so this was the original force, and the new offset distance, as I mentioned, it should be downwards, it should be acting like this. This is the original distance. So why it is downwards? Because the offset distance or the distance over which the couple acts, which we know, it will be like this. Okay, it will be like this. So the force should be acting from this point to a particular distance. From this point to a particular distance. It is all depending on the direction. So we get the value for